So one thing that really drew me to number theory as a graduate student was the interplay between arithmetic and analysis. And I suppose one of the first places that I saw this interplay was in something like the class number formula for abelian number fields. So on the one side of this formula you have kind of fundamental algebraic invariance, in particular the class number of the abelian number field. And on the right-hand side, or the other side of this formula, you have special values of L functions attached to the abelian number field. So yeah, somehow or another, these purely analytic objects, these L functions, seem to be encoding what appears to be purely algebraic information about the number field. And I was really fascinated by this. I thought it was really, really interesting, and I really wanted to know at that point, well, is there some fundamental connection between L functions and the algebraic object that they're attached to? Is there some really deep, intimate connection there, or is it just a trick in the bag that all number theorists kind of use? And I suppose the first really satisfying answer that I saw to this question was in Iwasawa's paper on p-adic L functions. So in this paper, Iwasawa shows how p-adic L functions, how they can be constructed from the Stickelberger elements, from the classical Stickelberger elements from cyclotomic fields. So that story actually begins with Gauss sums. So this is a classical Gauss sum. Here in this paper, we're going to assume that p is an odd prime, and we'll let k sub n be q adjoint zeta p to the n+1. So here L is the rational prime. It's just kind of an auxiliary prime. It's a prime that's split completely in k sub n, and this is a kind of classical Gauss sum attached to it. So the strange thing about these Gauss sums is that their factorization very weakly depends upon this auxiliary prime L. There's a part of its factorization that actually does not depend at all on L, and it's represented by a group ring element that we usually call the Stickelberger element, usually called the Stickelberger element attached to k sub n. And I suppose, yeah, since that element stays there no matter what auxiliary prime we use, and since there are so many, there's a sufficient number of these auxiliary primes L lying around, what we get then, what we're able to derive is what's called Stickelberger's theorem. So this is the statement that this Stickelberger element, this part of the factorization of this Gauss sum that doesn't seem to change, it actually annihilates the class group. And to boot, we can actually write it down explicitly. So it's a group ring element that only depends, it can be written down explicitly, it only depends upon the conductor of the field, and it gives us information about the class group. Now the thing that Iwasawa notices is that if chi is an odd character, not equal to the type Mueller character, then the chi parts of these, the coefficients of the chi parts of these Stickelberger elements, they induce what we call distributions or measures. So since the Stickelberger element is explicit, so is the distribution or measure that it induces. We can actually write it down explicitly like so. So here, if x is a p-adic integer, then s sub n of x is the integer between 0 and p to the n+1 that is congruent to x mod p to the n+1. W here represents the p minus first roots of unity in ZP, and kappa is a generator, some fixed generator of 1 plus p ZP. So this is the distribution or measure that comes out of taking chi parts of Stickelberger elements, and so it's one thing that, okay, great, these chi parts form a distribution. The really fascinating thing here is that if you take the Fourier transform of this distribution, what you get is essentially the p-adic L function of Leopold and Kubota. So in particular, if L theta minus chi of t, if this is representing the Fourier transform of our measure that we got from Stickelberger elements, from taking chi parts of Stickelberger elements, if we evaluate that at kappa to the minus s, we get exactly LPS chi star. The relationship between chi and chi star being that chi times chi star, that is the type Mueller character. So this is a great piece of mathematics. I was really kind of blown away by this when I first kind of read it. And I suppose, I always kind of make this bad joke to my students that mathematics is like Tinkerbell. You got to believe in it. And if you ever needed a reason to believe that L functions there was some deep connection, some intimate connection between L functions and the algebraic objects that they're attached to, then this work of Iwasawa's would be a great place to start. So the purpose of this paper is to show that Iwasawa's construction can essentially be duplicated on the plus side. So one question that naturally would rise up is, okay, well, we took chi to be an odd character before. What happens if we take it to be an even character? Well, unfortunately, the even parts of the classical Stickelberger elements, these are all zeros, so no really useful or interesting information can be obtained there. So the point of this paper is to actually construct analogs of Stickelberger elements, but that are applicable to the plus side, or phrased another way equivalently. What we do in this paper is we construct explicit annihilators in the vein of the classical Stickelberger theorem, construct explicit annihilators of the ideal class group of Kn+, the maximal real subfield of Kn, and we show that these they arise in a fashion that's very similar to the classical case. We show that they're coherent. The group ring elements that are doing the annihilating, they're coherent in towers, and so they induce measures and distributions, just like the same as in the classical case. And in fact, the Fourier transform of these measures, the Fourier transform of the measures obtained, these essentially give you twisted p-adic L functions. So one of the innovations of this paper is that not only do we duplicate all that classical theory kind of on the plus side or for Kn+, but we do so in a manner that's just as explicit as it was classically. So to give you an impression of what I mean, we actually start with kind of a real analog of a Gauss sum. So here we'll let K sub n plus, whenever we say that, we'll be referring to Q join zeta P to the n plus 1 plus. And this Gn plus of L, this is our real analog of a Gauss sum. So L is playing the same role as it did before. It's a rational prime that splits completely in Kn plus, kind of playing the role of an auxiliary prime. NB, this is like a truncated norm. Delta n of zeta L, well, delta n of t, that's a rational function where if you evaluate it at 1, delta n of 1 is actually a canonical circular unit of Kn plus. So in this paper we explain how the factorization of this element, once you kind of push it down into Kn plus, factorization of this element gives rise to explicit annihilators of the p parts of the ideal class group of Kn plus, very similar to the classical case where Gauss sums, the classical Gauss sums, their factorization actually gave rise to classical Stickelberger elements. Here are real Gauss sums, their factorizations give rise to explicit kind of real Stickelberger elements. So our real Gauss sums, they give rise to real Stickelberger elements, and the chi-star components of those Stickelberger elements gives rise to a distribution, which we can actually write down like so. So this is the explicit distribution you get from our explicit Stickelberger element. You actually get two different forms, two equivalent forms of this distribution. The other form is actually slightly more mysterious. It involves some p-adic logarithms of certain circular units, but they both differ. Both those distributions just differ by essentially an invertible distribution by convolution. And last but not least, when we take the Fourier transform of our real our distribution that we got from our real Stickelberger elements, we indeed get twisted p-adic L functions now. So this guy here, L theta plus chi star, this is the Fourier transform of the distribution we derived from our real Stickelberger elements, and when we evaluate that at kappa to the minus s, we get LP1 minus s chi star. So thank you for watching.